Okay, so let's now see how we can calculate the edit distance between two strings using dynamic programming. So let's say we are given two strings x and y. Suppose x has m characters and y has n characters. Okay, so the length of x is m and the length of the string y is n. And we want to calculate the distance between x and y. Now, the way we calculate the distance is by, of course, first defining what it is. Once we have the definition, then we can build an algorithm for calculating uh, the distance according to that definition. So here's the definition of edit distance. The edit distance between two strings x and y, or s1 and s2, is the minimum number of operations required to transform one string into the other. And these operations are of three kinds. You can insert a character, you can delete a character, or you can substitute one character by another character. Okay, so you can start from s1 and you're allowed to do these three operations in any sequence you want, so that you finally end up with s2. And there may of course be multiple possible ways to uh, transform s1 into s2. For example, a very simple way to do that is to just delete all the characters of s1 one by one and then insert all the characters of s2 one by one. But the edit distance is defined to be the minimum number of operations required to convert one to the other. So if there is a shorter path, if there is a shorter sequence of operations that can lead you from s1 to s2, then the edit distance will correspond to the shortest such sequence of operations. So here's an example. If you have a string DOF and a string DOG, then all you need to do to transform this string into this is to substitute F with G, and that constitutes a single operation, and so the edit distance between these two strings is 1. From cat to act, the number of operations you need is 2, right? Because the C needs to change to an A, one substitution. The A needs to change to a C, another substitution. So that's 2 substitution operations. From cat to dog, note that these 3 letters and these 3 letters are totally disjoint, right? So one way to do that is, of course, delete these 3 characters and then insert these 3 characters, but that would be 6 operations. A simpler way to do that is to just substitute C with D, A with O, and T with G. So that would be just 3 substitution operations, and that's the shortest sequence of operations you can have to transform cat into dog. So the edit distance is 3. Now there are variants of so this Levenshtein distance or edit distance that I mentioned over here corresponds to a definition where we have these 3 operations: insert, delete, and replace. There are variants of this distance measure where you're also allowed a 4th operation called transposition. Transposition is nothing but the swapping of 2 adjacent characters. Right? Sometimes when you're typing a particular word on your computer, you could type one of the letters before the other. Okay, you could accidentally swap the sequence just because you're typing so fast. For example, you may be trying to type cat, but you could type the A before the C, and that would make the string act. So if we allow transposition operations, then you just need one operation to transform cat into act, which is to swap C and A. So the edit distance in that case would be just 1. But for this lecture, what we're going to do is we're going to assume this simpler version of the edit distance, where we have only 3 operations. insert, delete, or substitute a character with another. So let's go back to that slide. Now we have to use dynamic programming. What that means is we have to build the solution bottom up, and we have to store the partial solutions. Okay. So let's define E of x comma y as the edit distance between x and y. Actually, more generally, just as we defined the Fibonacci number, let's define E of so let's take a prefix of x, okay, the first I characters of x, and let's take the first j characters of y, and let's define the a function called E, which is the edit distance between this string, which is the first I characters of x, and the first j characters of y. Now, what is E of so actually I can just call it E of I comma j here. Okay. So E of I comma j is the edit distance between the first I characters of x and the first j characters of y. So what is E of, what's the smallest possible value of the argument? It's just E of 0 comma 0. Right? Think of E as analogous to the Fibonacci function. Instead of the Fibonacci function, now you have the edit distance function. And instead of a single argument, you now have two arguments. Right? That's the only difference. So E of 0 comma 0 is the edit distance between the first 0 characters of x and the first 0 characters of y. So there are no characters. Okay, so you don't need to do any operations to transform an empty string into another empty string. So E of 0 comma 0 is 0. What about E of 1 comma 0? E of 1 comma 0 is the edit distance between the first character of x and no character of y, the empty string. So that will be 1, because you just need to do a single delete operation to transform this character into the empty string. In fact, for any E of k comma 0, where k is an integer, the edit distance will be k, because you just need to do k delete operations on these k characters of x to transform it into the empty string. And likewise, E of 0 comma k for any k is also equal to k, because in order to transform the empty string into k characters of y, you need to do k insert operations. So these are analogous to the base case of the Fibonacci series, right? Just as we said, Fibonacci of 1 is 0, Fibonacci of 2 is 1. These are the base cases for the edit distance function, where one of the arguments is a 0. Any questions about the base case?
No, sir.
Okay. So let's now try to calculate a formula for E of I comma j, just like we had the formula for the Fibonacci series. Of course, there the definition of the function itself gave you the formula of Fibonacci of n in terms of smaller values of the argument. But here we need to use the definition to derive a formula for E of I comma j in terms of E of smaller subproblems, in terms of the values of E for smaller subproblems. Once we have that definition, then we'll start from those smaller subproblems. We'll start bottom up and then build our way up to this particular value I and j. Right, we'll start from e of 0 comma 0. We'll start from these base cases and incrementally build up the solutions to larger and larger values of the arguments, storing those solutions in a table. Okay, in case of Fibonacci series, we stored the solutions in a linear array. Now we'll have a two-dimensional array, one standing for the index of the first argument and the other standing for the index of the second argument. So let's try to derive a formula now. Does anybody want to try this? What is the value of the edit distance for between the first I characters of x and the first j characters of y? The way to think about this is, let's think of three possibilities. Okay, how could we transform this into this? Think about the very last operation that you do. Okay, so the very last operation could be an insertion operation, it could be the deletion operation, or it could be the substitution operation. Right? So what if we just ignore the last operation? Everything that comes before the last operation would be a transformation from a smaller prefix of x into another smaller prefix of y. So let me put it this way. Let's actually think of this table. Okay, so this is the table for values of e. The rows correspond to the first argument, so we start from 0, 1, 2, 3 and so on, and the columns correspond to the second argument, 0, 1, 2, 3 and so on. And what we have seen is that the values of the base case here are exactly as f of k comma 0 is k and f of 0 comma k is k. Sorry, e of 0 comma k and e of k comma 0. Now also think of lining up the characters of x along the rows. Sorry, x. So I'm going to line up x1 over here, x2 over here, x3 over here, x4 over here. Similarly, y1 over here, y2 over here, y3 over here, y4 over here. Okay, I'm just laying down the characters of x. The first character of x along the first row, the second character along the second row, and so on. And the first character of y along the first column, the second character along the second column, and so on. So e of 1 comma 1 will be the edit distance between x1 and y1. Okay. E of 3 comma 3 will be, so the value that's stored here is e of 3 comma 3, and that's going to be the edit distance between x1 to x3 and y1 to y3. Now if I'm able to fill this table from, let's say in this particular order, I start from the first row which is already filled, then I start filling the second row, then I start filling the third row, then I start filling the fourth row, and so on. At the end, what is the value of the last row, the index of the last row? It's going to be x of m, and the index of the last column is going to be y of n. And this value that's stored over here is e of m comma n, which is the edit distance between the first m characters of x, which is nothing but the string x itself, and the first n characters of y, which is nothing but the string y itself. So this is the value we are interested in. But we will be building this solution bottom up, so that by the time we fill in this table, and again we are going to try to fill in this table so that the amount of time it takes to fill in any individual slot of the table is just a constant amount of time, just as in the case of the Fibonacci series. So that when we come to this particular cell at the very end, we'll just be using partial solutions stored else that we've already calculated and stored elsewhere in the table to just do one or two additions or comparisons and determine what the value here should be. So does anybody want to take a shot at what e of I comma j should be in terms of smaller values of I and j?
Sir, actually I wanted to clarify, like, how exactly would this be measured if there were unequal number of characters? Like, for example, if we had three, if m and n are not equal, like, how would this really happen? I mean, I'm not clear about that.
So this will be a rectangle in general, right? It could be a rectangle like this, or it could be a rectangle like this. I mean, this table, this is not a square table. It's a rectangular table. And it doesn't matter if the number of rows and the number of columns are not the same, because all what that means is that there will be some insertion and deletion operations necessarily.
Okay. Hello.
Yeah.
So, like, for example, if we have the words cat and network, like two different words,
Yeah.
and so, like, how would this, and let's say then, or rather, let's say it's cats and network, sir.
Cats and network.
Yes, sir.
Yeah. So you will build a table like this. I mean,
So
there should be an extra row and an extra column here. So, so this will be 1, 2, 3, 4, 5, 6, 7. There are 7 letters here, so there'll be 8 columns and 5 rows. So there'll be 5 rows, 8 columns, and you'll fill in the first, the 0th column and the 0th row in this particular way, and then you'll start building. So think about this, right? Think about this particular cell. What is the edit distance between x1 and y1? Just a single character x1 and a single character y1. What do you think is the answer?
x1 and y1. So, like,
It's a single character here, and it's a single character here.
So, are they the same characters?
Exactly. So you have to ask whether x1 and y1 are the same or not. Now, if they are the same, then
it's 0.
Then it's 0. But if they are not the same, then it's 1.
So how 1, sir? It's like, okay, replace.
Because you'll do one substitution. You'll just substitute x1 with y1. Okay. Now this is the way to. Here's how you should visualize this table. When think of focus your attention on this particular cell, right? This cell contains the value e of 3 comma 3 comma 3, right? It's the edit distance between the first 3 characters of x and the first 3 characters of y. Now when I move from this cell to this cell, right, I am adding an extra character of y, but I'm staying in the same row, so I'm not adding any extra character from the x string when I make a transition from one cell to the cell on the right. Right, so this move is analogous to adding y4, right, extending the y string by 1 without extending the X string. So it's like inserting Y4. Okay, so if I move from here to here, what I'm doing is I'm taking these two strings and I'm adding Y to the second string. Similarly, if I move down, I'm considering one extra character from the X string without expanding my problem size for the Y string. And if I move from one cell to the cell diagonally below and to the right, then I'm adding one character of Y at the end and one character of X at the end. So what we're going to do is, if we are at E of, let's say we've looked at the first I characters of X and the first J characters of Y. Suppose I know the edit distance between these two. Is it possible for me to extend, okay, let me put it in a different way. How do I calculate the edit distance between these two if I know the edit distance between I minus 1 and j minus 1? I know the edit distance between I minus 1 and j, and I know the edit distance between I and j minus 1. Suppose you're given these three values. Can you calculate what E of I comma j should be?
Sir, I have a question, sir. Like,
Yeah.
so is the edit distance between I comma j equal to edit distance of I comma j minus 1 plus 1? Will it be like that?
Okay, so that is a possibility. So one possibility is that in order to transform I into j, okay, in order to transform x of 1 to I into y of 1 to j, I transform x of 1 to I into y of j 1 to j minus 1. Okay, that's what this value is. And then I add the jth character. Then I do an insertion operation at the end.
So
Do you
could
see
you
that?
please, hello?
Yeah.
So could you please make that table for cats and networks so that we get an idea, because not kind of clear.
Okay. So let's make 5 rows. 1, 2, 3, 4, 5. C A T S N E T zero 1 2 3 4. Okay. Is this clear so far? So what is this value? It's the edit distance between the empty string on and the string netwo. Okay, so this is E of, right, this particular value is the edit distance between no character of x and the first 5 characters of y. And that's 5 because you just have to add 5 characters to the empty string in order to end up with netwo. And in general, what you have to think of is, if you're at an arbitrary cell, this is the edit distance between whatever, I mean, look at what characters are there to the top of this row in the X string, and look at what characters are there to the left of this column in the Y string. Okay, so this value is the edit distance between cat and NETWOR. The first 3 characters of X and the first 6 characters of Y. Is that clear? Now, what you have to think about is, how would you calculate this value if you were given these 3 values? Look at the 3 cells, the one on the left, the one to the top, and the one over here. All these 3 cells correspond to smaller subproblems. Right? This cell corresponds to the same prefix of X, but with one less character of Y, without this R. Right? This cell corresponds to the edit distance between the same prefix of Y, but with the prefix C and A of the string X. And this cell corresponds to the edit distance between a smaller prefix of X and a smaller prefix of Y. Okay, one character from both strings has been removed from the end. So what we have to ask is, what is the very, okay, let me try to explain it in a different way if you're not getting this. Think of an insertion operation. So let's say we insertion of a character So let's look at this operation. We are going to start off with this string X from X1 to XM, and I'm going to denote a deletion operation in this particular way. Okay, so if I delete a character xi from the string X, I'm going to denote it like this. If I insert a character yi, I'm going to denote it like this. And if I substitute xi with yj, I'm going to denote it like this. So think of aligning So let's take the example you gave, CAT and networks. Okay, so here's what I could do. I could delete the 3 characters CAT and then add these 8 characters, in which case I'm going to denote it like this. So look at the sequence of operations I'm doing here. I'm deleting the C, I'm deleting the A, I'm deleting the T, I'm adding an N, adding an E, adding a T, and so on. Another way I could have done this is, I delete the C and A, then I insert an N and a T, and an E, and I keep the T as it is, and then I insert a W, right? So I'm doing 2 deletions followed by 2 insertions followed by 5 insertions. I'm keeping the T as it is. So how do I align? So how do I draw this kind of a picture where I need to, note that in this row you need to have CAT, but interspersed with some blanks if you have a deletion operation. And likewise, you need to have the second string here, but interspersed with some blanks corresponding to, um, actually these blanks correspond to deletion of this character, and these blanks correspond to insertion of the characters in this string. So effectively you want an alignment of these two strings such that you minimize the total number of cells from left to right, the total number of operations. Each of these is an operation. This one is not, but so what I'm going to do is I'm going to give you the formula and try to see if you can see why this formula is true. Plus so E of I comma j is the minimum of these three values. Either it's E of I comma j minus 1 plus 1, or it's E of I comma I minus 1 comma j plus 1, or it's E of I minus 1 comma j minus 1 plus either a 0 or a 1 depending on whether the last character in the sequence X is the same as the last character in sequence Y or not. Okay. This row corresponds to insertion of y sub j. This corresponds to let me write it in a different slide. Actually, let's go back to this slide. You recall this picture that I showed? E of I comma j will be either this value plus 1 or this value plus 1 or this value plus either a 0 or a 1 depending on whether this character is the same as this character or not. And that the reason for this is so again let's look at three possibilities. Okay, case 1 is when the transformation of x1 to xi into y1 to yj is going to happen in such a way that in the very last step we will delete xi. Case 2 is a path from x1 to xi to y1 to yj in such a way that in the very last step, in the last step here we are deleting xi, in the last step here we are inserting yj, and case 3 is when in the very last step we substitute xi with yj. Okay, there are only these three possibilities. We are going to operate on the string from left to right. Okay, so our last step will be an operation on the extreme right of the, whatever string we are working with. So either we could be deleting xi at the very end, or we could be inserting yj at the very end, or we could be substituting xi with yj. Can you think of any other possibility for the very last step?
Transpose yi and xj.
So we are not going to work with transposition here. As I said, we are dealing with the Levenshtein distance, which is a simpler version of the edit distance. So transposition is going to make this even more complicated. So let's just have, we only have three operations: insert, delete, and substitute. Now here's the point. Consider any of these three cases and think of all the operations. So let's say we look at case 1. At the very end, we are deleting x sub I. Okay, that means before this we would have transformed x1 to xi minus 1.
Sir,
Yeah,
excuse me. Can we give a 5 minutes break for them so that we'll
sure.
resume back after 5 minutes?
Okay.
Thank you.
So here's another try to try to explain it in a way that you can visualize what exactly is going on. Think of starting from this string x, which you want to transform into the string y. Okay, and the way we're going to transform it is we'll start from the left. Okay, we are initially starting with the string x. Okay, and we are going to massage the string in some way through a sequence of operations, so that at the end of it, after we've reached over here, we are going to have y instead of x over here. Right, so we are starting from the left end, we are doing something to x, and finally, character by character from left to right, so that by the time we reach the end at the right, this won't be cats anymore, this is going to be network. Okay, so what exactly are we doing? We are starting from here, and in each step we have three choices. Either we could add a character at the location where we are, or we could delete the character of x, or we could change the character, the next character of x into some other character, right? So at the very beginning I have three choices. Either I can delete this c, or I can change this c into some other letter, or I can add something before this c. I can insert a letter before this c. Now what we will do is we will insert an n. That will be our first operation. Then we will insert an e. That will be our second operation. Then we will delete this c. We will delete this a. Note that we are moving from left to right now. We'll keep this t as it is. And then after crossing this, we will add a w. Then we will add an o. Then we will add an r. Then we'll add a k. And then we'll delete this s. And so when we reach the end over here, we have network instead of cats. This was just one possible way to change cats into network. There are other possible ways. One way was to start from the left, just delete c, delete a, delete t, delete s, and then add n, e, t, w, o, r, k, and then end. Okay, another possible way was, so we start from the left and we just we just add n, e, t, w, o, r, k, and then we delete c, a, t, s, and then we end. So think about the various ways in which you can transform cats into network. There are many possible ways. But what I'm saying is, regardless of how you do it, at the very end, the very last operation that you do at the end can be of three types. Either you can add a letter, and if you add a letter, note that this letter you're adding will have to be the last character of y, right? It will have to be k in this case because you want the string network to be there. So if your last step is that of adding a character, that character must be k, right? So if you're adding a letter, it must be y sub n, the last character of the string y. The other operation that you could that you could potentially end at is to delete a letter. And if you delete a letter at the end, the letter must be the last character of the string x, right? For example, here we ended with deleting this s, right? Because if you're deleting a character, it must be from the string x. You won't be deleting anything from the string y because you want y to be there. And if you're adding characters of y and then deleting characters of y, then you're undoing the work that you just did, in which case you're not following the shortest sequence of operations, right? So the character that we must be deleting at the end, if we end with a deletion, must be the last character of x. A third possibility is that we substitute x of m with y of n, right? We could end this um, this transformation with a substitution operation, and here's how you could do that. Let's say we have cats at the end, so I'm going to add, so at the beginning I'm going to add NETWOR, then I'll delete C, I'll delete this A, I'll delete this T, and then I'll substitute this S by a K. Okay, so I'm changing the last character of X into the last character of Y. That's how I'm ending. Is this clear that these are the only three ways in which we could end? Of course, by substitution, if the last character of X is identical to the last character of Y, then we won't be doing any operation as such. You can think of substituting x of m with y sub n, but really it's not a substitution operation. You're just substituting that character by itself, in which case, it's not really going to cost you anything. So the point is that these are the only three ways, these are the only three possible last steps that the very last step that you take has to be one of these three, and everything before that very last step must be done in the optimal way if the overall operation is to be optimal, right? So if I'm going to be adding a letter, the last character of y at the end, that means so far what I've done is I've transformed x into the first y minus the first n minus 1 characters of y, right? If my last operation is that of adding the last character of y, what would I have done before it? I would have transformed x into the first n minus 1 characters of y. That is why in the very last step I'm adding the last character of y. And the claim is that this transformation, which would have happened before the last step, itself must be optimal for the entire operation from the transformation from x to y to be optimal, right? If we want this to be optimal, and if the very last step of that optimal path involves adding a character to y, the last character of y, that means everything that went on before it must also be done in the optimal way. Because if it was not done in the optimal way, then I could do it in the optimal way and reduce this overall cost of the transformation. Right? So it's like, if you um, if the shortest path from say Bangalore to Delhi is through say Bhopal, right? Then it must be the case that the path you took from Bangalore to Bhopal must be the shortest path from Bangalore to Bhopal. Because if there was another shorter path from Bangalore to Bhopal, then you would have taken that one. Right? If you've done a course on algorithm, you should be familiar with, um, how do you calculate the shortest path. There also you look at, you can analyze it in the following way, that if I have to go from city A to city B, and city C is the very last city I travel through before I reach city B, and this is the shortest path from A to B, then it must be the case that this is the shortest path from A to C. Because if there was a shorter path from A to C, then I would have followed that path and then followed C to B, and then I would have gotten shorter path from A to B. Right? So the shortest path from A to B must satisfy this property, that it must also include the shortest paths from A to C and the shortest path from C to B. Otherwise, this entire thing won't be the shortest path. In a similar way, if the last step of our transformation is this particular operation, then whatever happens before this operation must also be done in the shortest possible way. Similarly, if the last operation was a delete operation, that is, if you are deleting the last character of x, then we also have to minimize the work done till that point. And if the last operation was to substitute x sub m with y sub n, then excluding this operation, before this operation was done, we should have done everything up till that point in the best possible way. So that is how we end up with this equation, where E of m comma n, okay, which is the edit distance from x to y, right? Remember, x is x1 to xm and y is y1 to yn. The edit distance from or the number of steps, the minimum number of steps required to transform x into y must either be the minimum number of steps required to transform x into y1 to yn minus 1 plus the cost of adding a letter to y. That's one possibility. Or, okay, case 1, this is the minimum number of steps required to transform x into y1 to yn minus 1 plus the cost of adding this letter yn, or doing this insertion operation, which costs which is a single operation. Or case 2, it could be the cost of the minimum number of steps required to transform the first m minus 1 characters of x into y, followed by a delete operation on the very last character of x at the very end. Right, so case 2 could be transform the minimum number of steps required to transform the first m minus 1 characters of x into y plus the cost of deleting that very last character of x. And in case 3, what we are doing at the end is we are substituting x of m, the last character of x, with the last character of y. So that means before that we would have transformed the first m minus 1 characters of x into the first n minus 1 characters of y. So that at the very end we are doing a at the very last operation is a substitution operation, where we are substituting the last character of x with the last character of y. And this would count as 1 if the two are not the same. If x sub m is not equal to y sub n, that means this is an actual substitution of one character into a different character. Or it will be 0 if x sub m is equal to y sub n. That means this is not really an operation. We are just changing the character into itself, which is equivalent to just ignoring it. Now, which of these formulas will actually be the value of E of m comma n? Because these are the only three possibilities. The minimum of these, right, at the edit distance is the minimum number of steps required to transform x into y. So whichever is the minimum of these three, that's going to be E of m comma n. Are there any questions about this? Forget about the table for now. Just look at this formula or this recurrence. This is analogous to fib of n being fib of n minus 1 plus fib of n minus 2. Any questions about this? Do ask right now.
So are we always deleting the characters of x at the beginning? So
Not necessary. You could also just substitute it, right? So if I want to do cats into network, one way to do that is to change, to start from here, change this C into an N, change this A into a T, change this T into, let the T remain as it is, change this S into a W, and then add O, R and K. You don't have to necessarily delete characters from X.
okay.
But if you look at the very last step, either we are adding a character of Y, or we are deleting a character of X, or we are substituting the last character of X with the last character of Y. No matter which of these three cases you apply to, you're always dealing with the last character of one of the two strings. Sometimes both in case of a substitution operation. Now if you have this formula, if you have any questions about this formula, do ask right now.
So yes, so are we always trying to go from left to right in this string substitution? Like, are we trying to build it from left to right always?
You could imagine, you could define the indices from, starting from here to, so the reason I'm going left to right is because I'm assuming that we are dealing with prefixes here. You could define an analogous formula for suffixes where we could go right to left and do something like this. The formula there would also be the same, except that you'll probably start your indices from here 0 and go up to m and n over here. So in that case you would say that if you go from right to left, then the very last step will either be deleting the first character of x, or adding the first character of y, or substituting the first character of x with the first character of y.
So it's always like in one direction. I'm just trying to ask that, like, doing it in some random order it's not like that, is it?
Well, you can think of doing these steps. Think of them as doing only left to right or right to left. In fact, if there is an optimal path, right? If there is an optimal path, it's always possible to implement that optimal path from left to right. Think about that for a minute. Because as I said, if you diagrammatically depict a deletion operation from X like this, so let's say this corresponds to deleting C, this corresponds to deleting A, this corresponds to deleting C, this T, this corresponds to adding an N, this corresponds to adding an E, this corresponds to adding a T, and so on. You can implement this operation first, then you do this operation, then you do this operation, then you do this operation. It doesn't matter. As the important point is that this is the exact sequence of operations. You can implement them in any order, but just for visualization purpose, just think of it as being implemented from left to right. That will help you to understand the formula. What I'm trying to do is I'm trying to break down the problem into a slightly smaller subproblem, because that will help us derive this recurrence equation for the larger problem. And in order to break it down into a smaller problem, let's just let's just do it in a way so that the difference between the smaller problem and the main problem is only at the right end, because then that will help you visualize what's going on. Now, if you agree with this formula, then if we now go back to this table, if we go back to this table, and if you look at, let's actually look at this. So let's say, yeah, let's look at this. This is what we want to calculate, E of m comma n, right? It's the edit distance between the first m characters of x and the first n characters of y. Now E of m comma n is expressed in terms of E of m comma n minus 1, which is nothing but this particular cell, the value in this particular cell, and E of m minus 1 comma n, which is the value in this particular cell, and E of m minus 1 comma n minus 1, which is the value in this particular cell. Okay, so if I have these three values, I can calculate what this value is, because this value will be the minimum of three possible values: this value plus 1, this value plus 1, and this value plus either 0 or a 1, depending on whether this character is the same as this character or not. Right? So as I said before, when you think of, so if you visualize this process that I described, where you start from x and you're going from left to right, and then you're ending with, at the end, when you reach the right end, you're ending with y. You can visualize that operation as starting from this cell and following a path down this table and ending up here. Okay, that's why I'm trying to, I asked you to visualize it that way, because you can map each step in that path to a move in this table, either a move to the right or a move down or a move diagonally like this. So if my first operation was adding the character of y, I would be moving to the right. That would be like moving one step to the right. If my first operation was deleting or substituting the first character of x with the first character of y, that would be like taking a diagonal step, because now this cell tells me the edit distance between this string and this string. Okay, so this is x. Remember that this is x, and remember that this is y. And when I take a step to the right, that is like writing this. Okay, when I take a step to the right, I'm not adding any new character of x, but I'm adding this new character of y. So I'm not adding anything to x, I'm adding this. So this is like adding a character of y. When I take a step down, I'm including a character of x, but not including a character of y. So that is like this operation, which is really a deletion operation. And when I move diagonally down, I'm including this character of x together with this character of y. So that would be like doing this substitution operation. So what I would say is when you go back, the dynamic programming is not easy to get when you come across it for the first time. But try to see how this step, the sequence that I described, where you start from the left end of x, and then you do the sequence of operations, and you end up with at the right end, and you'll be left with y here. Try to see how every step of that operation maps to a hop or one single step along this table. You're starting from here and you're ending here. At the very end, when you terminate, you've calculated E of m comma n, which is the edit distance between this string and this string. When you are at this cell, you've calculated the value, which is the edit distance of this string with this string. And when you're at the beginning, you're at 0. So this value is nothing but the edit distance between nothing here and nothing here. So think of how every operation you do maps to a particular step in this table. And the claim is that if you look at the formula, you'll see that the value in any cell can be calculated based on the values in the 3 cells adjacent to it. Just by adding a 1 for these two values and adding a 0 or a 1 depending on whether this character is the same as this character or not, and take the minimum of these three, or those three values, and put it here. Now how do we go bottom up? Let's say we fill in this table like this, in this particular order, row by row. If we fill in this table row by row, whenever we come to a cell, we would already have filled in the three boxes to the left and to the top and to the top left of this cell, no matter which cell we come to. If we are filling in this row by row like this will always be the case. So whenever we come to any cell, we can just look at these three values, add 1 to this, add 1 to this, add 0 or 1 to this, see which of those three results is the minimum, and put the minimum of those three into this cell, and then move to the next cell. So you can fill in the numbers here row by row. And actually there are multiple ways to do this. You can also fill in the numbers column by column like this, from top to down. Again, if you follow such a path, then whenever you come to a cell, those three values will already be available to you. You can also go diagonally like this. I mean, you can fill in the cells diagonally like this. But whatever you do, the point is that for filling in the value of any cell, you just need 3 or 4 additions or comparison operations, so that if there are m rows in this cell and n columns, time big O of m times n, in time proportional to n, you can fill in this whole table and get the value of the edit distance between the two strings.